Howdy, it is your friendly neighborhood physics teacher with your part 2 of your review. So now we're getting into the multiple choice section of your review. Now, again, these questions aren't exactly like your test, but they should be very similar. So you can get the idea. So if you haven't watched my earlier video, I did the kind of free response conceptual questions before. And now I'm about to do some multiple choice questions. We're still on projectiles, and it is a mix of horizontal and angular. So let's get right to it, shall we? So a 5-kilogram sphere initially at rest is allowed to fall towards the earth for a time of 5 seconds. Now it's telling you, hey, you're going to do some easy math. It's saying you use gravity as 10. Its velocity at the end of this time is. So it gives us our mass. It says it's initially at rest. So remember, that's our V IY equals 0 meters per second. And it says the time is 5 seconds. It's telling us our gravity. Only a little correction there. You have to remember that gravity is negative. And we're looking for our velocity at the end. So we're looking for our velocity final. Whoops, I keep forgetting to put final. Velocity final in the y. So if we look at our equations and think about what we're given, we can actually use our VFY equals our VIY plus AT. So we throw in what we got. We know that's 0. We're going to use negative 10 times our time. So that just gives us negative 50 meters per second. And know that your V final Y. And remember, that negative is just direction. That negative is just direction. And negative means down. Equals down. So do we have a 50 down? Yep, we do. Yay! So our answer would be 50 down. So we couldn't use any of our other equations because we don't have our delta y, and we don't have our delta x, and we don't have our velocity in the x. So, and it says the reason I knew to use the y is because this little thing right here, it said fall towards the earth. So falls towards the earth, again, that means down. So we're going down, that's in the y direction. Woohoo! So a projectile is fired at an angle of 45 degrees above the horizontal. So you have the horizontal just above. So that means that's 45 degrees. Assume that the air resistance is not significant, so we ignore air resistance. While the projectile is in flight, the acceleration remains constant. Now, what is the acceleration, you might ask? Well, the acceleration is just, so your acceleration is just gravity. So is that constant? Yes, it is. A soccer player kicks a ball with an initial velocity at 10 meters per second at an angle of 30 degrees above the horizontal. The magnitude of the horizontal component of the ball's initial velocity is. So we're going to come over here and draw a triangle. Because anytime it gives you a velocity with an angle, you have to draw a triangle. I repeat, anytime it gives you a velocity with an angle, you're going to have to draw a triangle. And that velocity it gives you is going to be at your hypotenuse. So it's asking for the horizontal component. So it's asking for this component right there. So that would be our cosine angle equals your adjacent over hypotenuse. We want adjacent, and so that it will end up being 30 equals adjacent is x over hypotenuse times 10. So your Vx will end up being your 10 cosine 30. That's when you pull out your handy dandy calculator and do 10 cosine of 30 degrees. Make sure you're in degrees mode. And your velocity in the x direction is 8.66 meters per second. So do we have an 8.66? Well, we had an 8.7. So, woohoo! Next question. A machine launches a tennis ball at an angle of 25 degrees above the horizontal at a speed of 4 meters per second. The ball returns to level ground. Which combination of changes must produce an increase in time of the flight of a second launch? Okay, so we're trying to figure out which of these combinations would increase the time. Okay, increase the time. So a couple of things to think about. What equations do we have that have time in it? What equations do we have that have time in it? So we have, we're looking at it, we have VFY squared. Nope, that one not squared. Squared doesn't have it, but VFY equals VIY plus GT. We have delta X equals VXT. And we also have our delta Y equals VIY times T plus 1/2 GT squared. So those are our equations that have time in it. So those are the big things that can affect. So decreasing the launch angle. Now, if we decrease the launch angle, let's think about what the launch angle shows us real quick. So we have a launch angle. I'm going to get a color over here. Okay. So we have a launch angle. So as we decrease the launch angle, what do you notice about your velocity in the y? It gets smaller and smaller and smaller, right? So if you decrease your velocity in the y, if you're decreasing your velocity in the y, would that increase your time? Hopefully you said no, because height affects time. Height affects time. So, decreasing angle would not work. So it doesn't even matter what the other thing is, because decreasing the angle. Decrease the angle? Oh, no. So now we're increasing. So we know increasing the angle works. We know we're down to C and D. So now it's decreasing the ball's initial velocity. So again, we're changing the initial velocity. So if we change the initial velocity, that will change your velocity in the x and velocity in the y. So if you have a smaller hypotenuse, that means you have a smaller of the legs. So again, that wouldn't work. So we're looking at, if you increase the angle and increase the ball's speed, you should increase your velocity, initial velocity in the y, and everything would be good. So that's a conceptual problem. A golf ball is propelled at an initial velocity of 6 meters per second at a 37 degrees above the horizontal. The horizontal component, the ball's initial velocity is, so it's just like 21. It's just like 21. We're going to have to, since it's at an angle, we're going to have to make a triangle. So this is 60, our angle is 37, and we're looking for our horizontal component. So again, that's cosine, so it'll end up being our velocity, cosine of our angle. We know our velocity is 60. We know our angle is 37. So we plug that into our handy dandy calculator. And we get 47.92 meters per second. Any of those answers pretty close? I'd say that would round up to 48, wouldn't you? Yay! Cool. So, now on 24. A projectile is fired with an initial velocity of 120 meters per second at an angle theta above the horizontal. If the projectile's initial horizontal speed is 50 meters per second, what is the angle? So, still it's the same thing. We're having to draw a triangle. But in this case, we don't know our theta. We know our hypotenuse and we know our horizontal component, but we don't know our angle. So remember, we would be using our cosine. So cosine theta equals opposite over hypotenuse, but we need to get theta by itself. To do that, we have to take the inverse of our cosine. So do inverse cosine. Our adjacent is 55. Our hypotenuse is 120. So you do the inverse. So that's second cosine of 55 divided by 120. Handy dandy calculator gets you an angle of 62.72 degrees. So that would round up to be about 63 degrees. Now, a golf ball is hit at an angle of 45 degrees above the horizontal. What is the acceleration of the golf ball at its highest point? I know I've done this a lot. You think this is important? The answer is yes. So remember, acceleration is just your gravity. So it's negative 9.8 meters per second squared. The negative is just a direction. So in its direction is down. So your answer should be 9.8 meters per second squared down. A ball is thrown horizontally at a speed of 24 meters per second from the top of the cliff. If the ball hits the ground 4 seconds later, approximately how high is the cliff? Let's draw it out so we can visualize it, shall we? So our cliff, we have a ball. So we're looking for how high. So we're looking for a delta y. But we know the ball is about 24 meters away. And it took about 4 seconds for it to fall. So we know, and other things we know, but it's not given. We know that our v IY is 0, because that's a secret given, and we also know gravity is negative 9.8 meters per second squared. So we're looking for our delta y, and there's actually an equation for that. GT squared. Yay! So it's pretty easy. We know gravity is negative 9.8. We have our time, which is 4 seconds. So this problem gave us extra information. We didn't need that information. Sometimes problems do that. They give you extra information that's not needed, and they try to throw you off. So your height ends up being negative 78.4 meters. Now remember that negative is just telling you the direction. The ball is going down. But if it's asking for the height, you just get 78. Very good. So a 0.2 kilogram red ball is thrown horizontally at a speed of 4 meters per second from a height of 3 meters, and a 0.4 kilogram green ball is thrown horizontally at the same height with a speed of 8 meters per second. Compare the time it takes for the red ball to reach the ground. The time it takes the green ball to reach the ground. So remember, what is the biggest thing? What affects time? Height affects time. Height affects time. Height affects time. So what about the height? What's so special about the height? Same height. So since same height, what does that mean about the time? It's going to be the same, no matter how much it's going in the x direction, because these velocities here are moving in the x direction. X direction. X direction. Doesn't matter how much is moving the x direction. Height affects time. Same height, same time. So the ball is thrown at an angle of 38 degrees to the horizontal. What happens to the magnitude of the ball's vertical acceleration during the total time interval of the ball in the air? So again, acceleration is what? It's gravity. Gravity. So does gravity change? No, it's negative 9.8 meters per second squared. So it remains the same. Yay! So now we're getting to the universal gravitation part of our review. So we have a few multiple choices. So we have 5 multiple choices. Cool. We had more than that. Awesome blossom. We have 5 multiple choices. Sworn we had more than that. That's okay. So Newton's universal law of gravitation states that the gravitational force between the two objects is blank proportional to the product of the masses and blank proportional to the square root of the distance between the objects. So it kind of helps if we write down the equation. So let's write down the equation, not in yellow. So equals our constant, m1, m2 divided by r squared. So, and our choices are directly proportional and indirectly proportional. So remember, directly proportional, I'm here, put a D, directly proportional means if one goes up, the other goes up. Indirectly proportional means if one goes up, the other goes down. So we have to think about this mathematically. So if mass goes up, would that make the overall number bigger or smaller? It would make our overall number bigger. So that would be a direct proportional. So we can mark out C and D. Next one, as distance increases, would our numbers get bigger or smaller? Our overall number would get smaller. So that would be inversely. So our answer becomes B. Yay! Okay, so if the mass of the moon is doubled, the mass of the Earth remains the same. What happens to the gravitational force between them? So again, we look at our equation. Go away. Okay, fine, I'll just use it. So, not yellow. Our force of gravity equals big G, m1, m2 divided by r squared. So it's saying what happens if one of our masses is doubled? What would happen to our forces? So if this is doubled, it's being multiplied by 2. That means the whole entire system is being multiplied by 2. So to keep it balanced, I would have to multiply my force by 2. So that means our force is doubled. So 2 students are sitting 1 meter apart. One student has a mass of 60 kilograms. The other has a mass of 95 kilograms. What is the gravitational force between them? Oh, one more. Let's give me some work room here. So again, remember the biggest issue we have in this unit is plugging in. So mass 1, mass 2 over r squared. So our force of gravity, our g is just 6 point, I just wrote a g because I said g. We were talking about multitasking there, doesn't work. 6.67 times 10 to the negative 11 times 60 times 95. We're going to divide that by 1 squared. Now remember, when you plug into your calculator, go ahead and put 6.67 e negative 11. Plug it in like that into your calculator. So, and then we plug it into our handy-dandy calculator. So you got 6.67, do second comma, which will give you that e, negative 11, times 60, times 95, divided by 1 squared, and you get 3 point, you end up getting 3.80 times 10 to the negative 7. That is your force of gravity. Oop, running out of the room. That is your force of gravity. It looks like the answer is dun 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 A. Yay! So, if the mass of the moon and Earth remains the same, but the distance between the two is cut in half, what happens to the gravitational force? Again, so let's pull out our equation. M1, M2 divided by r squared. So now we're doubling. No, it's saying between the two is cut in half. So for some reason, the moon gets really close to the Earth. So we're taking our distance and cutting it in half. So we're cutting it in half. So remember that 2, that squared's got to go to both numbers now. So it ends up being r squared over 4. But when you do a divide over divide, you're really just now saying, and I'll actually keep it in the color so you don't get confused, force of gravity, g, m1, m2 divided by r squared. But when you divide a divide, it's just a multiply. So you're actually increasing it by 4. When you decrease, remember, it's an inverse relationship. Going back here, it's an inverse relationship. So as your distance decreases, your force increases. So your distance decreased, your force increased. Compare the magnitude of the force the Earth exerts on the moon to the force the moon exerts on the Earth. So basically, it's going to end up being the same. Because no matter if you put, because of the masses, since it's being multiplied together, so let's look at the equation. G equals G m1 m2 divided by r squared. No matter which way you write it, even if I write it m2 m1 divided by r squared, you're going to end up getting the same. Because they're just being multiplied. So the amount of force that the Earth is putting on the moon is the same amount of force the moon's putting on the Earth. That's where Newton's third law comes into play. For every action, there's an equal but opposite reaction. So I hope that helped you review for your test. Again, remember that you have a website and a video for each type posted onto Schoology. In the little red folder that says review for the 2D motion review. Please excuse my computer giving me all these reminders. And don't forget to email Miss Heath or Miss Verona if you need some help. Hopefully you have an absolutely wonderful day.